my paper consists these 5 parts. The first part is about the measured result for the main characteristics of the spalling. The studied locomotive is with the CO2CO bogie, the 3-axle bogie, and over 500 wheels were observed and in different running distance and routes. As our large observed results and 3 types of cracks are commonly observed. And the first picture is the first type of the cracks. It's located on the field side of the well, and mainly in the 75 to 100 millimeters from the flange back. These cracks always uniform around the wheel circumference. The second types of cracks are located on the wheel center, about 65 to 90 millimeters from the flange back. And these cracks also always shows the transverse direction. And the third types of cracks also the transverse cracks, but its location is nearing the flange throat. The wheel turning depends on the depth of cracks. So the measurement was also carried when the wheel is turning. The first picture is the damaged wheel with obvious cracks on the surface, and almost these 3 types of cracks were observed on the surface. And after turned 1 millimeters, only the cracks around the wheel center left. But another 2 types of cracks was eliminated. And after another 7 millimeters turned, the cracks nearing the wheel center are still not eliminated. And finally, the totally turned depth is 12 millimeters. So this can be shown that these transverse cracks nearing the flange, nearing the wheel center, are propagating deep into the material. This greatly shortens the service life of the wheel. So our study is mainly focused on these types of cracks. The development of this, the focused cracks were also tracing. The wheel surface condition was observed for the same wheel of the same locomotive. After 40,000 kilometers, it can be found on the surface. The small peeling pieces can be found and occasionally appeared. And after 80,000 kilometers, these small pieces spread all over the wheel circumference. And with the increase of the running distance, large spalling pieces can be found obviously, and obvious cracks also found on the surface. The next part is the potential causes based on the compared measurement. The first one is the wheel sliding or idling. This cause is proven by the comparison study between 4 types of locomotive used on the same line, as listed in this table. The study on the Type C locomotives are both with CO2CO bogie. Their surface shows obvious spalling, but for the Type A and Type B locomotives, they are with double BO2BO bogies, and their surface are rarely surfing the spalling. It is known that the locomotive's traction or braking capacity was big influenced by the big limited by the real friction coefficient. And in this condition, the maximum traction and braking forces can be calculated. For the studied and Type C locomotives, their traction and braking forces are smaller than the Type A and Type B locomotives. And two types of locomotive surface also observed after running the same distance. And the first picture is the surface condition of seal bogie. It can be found that there are obvious cracks on the surface. And the cross 2 is the small radial curves. Another word is the locomotive curving performance. This was proven by the compare the wear surface condition used in two different lines, but the locomotive was the same. It can be found that in line A, sharp curves in range of 400 to 500 meters is much more in line A. But in line B, there are more curves with radius greater than 800 meters. After running the same distance, in line A, with lots of small curves, more serious wheel trend spalling. But in line B, the wheel surface is relatively good. The wheel turning records from the locomotive depots is also consistent with the observation. Okay, the third part is the real-wheel dynamic interaction to give some evidence for the measured result. Two types of locomotives was chosen to simulate, and the model was based on the vehicle track coupled dynamics. We do a lot of simulations, and the real vertical force, lateral creep force and creepage, and the longitudinal creep force and creepage were compared. In the straight line, the locomotive with seal to seal bogie, its longitudinal creep force and creepage are greater than the locomotive with double bill to bill bogie. For the small curves, although the real longitudinal creep force is relatively same, but it can be found on the real longitudinal creepage. The locomotive with seal to seal bogie is much greater than the locomotive with double bill to bill bogie. So how to decrease the longitudinal creepage? We analyzed the friction coefficient and the curve radius. It is true that with the increase of the real friction coefficient and the real longitudinal creepage decreased obviously, and in large curves, the real longitudinal creepage is decreased significantly. So the real friction coefficient and the curve radius both have the obviously influence on the real longitudinal creepage. And for the studied locomotive running in the fixed line, its curve radius are not easy to change, but it can change the real friction coefficient on the tread contact area, which is hoped to reduce the wheel tread spalling. The fourth part is the case study and give some relationship between the crack direction and the creep force. We chose the case, the locomotive passing the small curves with braking force. can we find that for the front and middle wheel set, there moves outside the curves. And for the rear wheel set, it moves inside the curve. So the wheel-rear contact position is shown in the second picture. It can be found for the inner surface, inner wheels of the front and middle wheel set, and the outer wheels of the rear wheel set. Their wheel-rear contact position is located on the severe damage band, especially for the rear wheel set. So it's the creep force of the rear wheel set was also simulated when passing curve with braking force. It can be found that with the increase of braking force, its direction, the blue line, its direction was of the resultant creep force of the rear wheel set is greatly consistent to the running direction, and which is likely to producing the transverse cracks. This is only one case study. A lot of cases was also in simulated. So this is my conclusions. The wheel-trad spalling is a very difficult problem, especially for the heavy haul locomotive, because there its traction and braking force is greater. So, in my opinion, I think to decrease this problem, it is first step to find out the main causes. So this study is about our work, and we hope to decrease the wheel-rear dynamic performance, and especially for the wheel-rear relative sliding and idling. Okay, thanks for your attention, and I hope your kindly suggestions.